Hi, we're going to talk about implicit differentiation today, which uses the chain rule, which we should have some competency in from last time we discussed differentiation. So I wanted to talk about what it means to be implicitly defined, okay? Back in pre-cal, we talked about functions that were implicitly defined, something like x squared plus 3xy plus y cubed equals 7. This is implicitly defined. It's not explicitly solved for y. So it's implicitly defined, meaning there is some function of y implied. You'd have to solve for y, which would be really next to impossible in this case, because you'd have to isolate the y, and that's would be really difficult to do here if possible at all. But we have some functions that are embedded in here. This one would be y equals x squared plus 7x plus 3. This one is explicitly defined because it's y equals. It's a function as y is a function of x. Okay, but if we were to look at this curve, if I go to my Desmos here, y equals x to the second plus 3xy plus y to the third equals 7. Oops, I can't type this morning. That's what the curve looks like. And you can see on this curve that it has a vertical tangent here, and it's got a horizontal tangent up here somewhere, and another vertical tangent. So there are slopes to be found to these curves. These curves have rates of change, and we need to be able to have some vehicle or some way to be able to find their slopes. Okay, so that's what we're going to do today. And Chrome is being ornery here. It wants to always stay on top, so we're going to solve that. Okay, now we're going to talk about an implicitly defined function that we're very, very familiar with. I mean, and it's one I hope that when you see it, you will know right away. X squared plus y squared equals 1. Now, not all at once. That's the unit circle. You're right. It is the unit circle with a radius of 1. And most implicitly defined functions are, when you graph all the functions that are implied inside, turn out to be relations. Now, this right here is not explicitly solved for y, so it is implicitly written. And we can, however, solve it for y, because this is an easy one to do. So solving for y, what can we do? We can say that y squared equals 1 minus x squared by moving the x squared over to the right side. And we can say that y equals the square root of 1 minus x squared, or y equals the square root of 1 minus x squared, but it's negative, right? Because we have to consider the negative one. Now, on this curve, the positive y equals x, the square root of x, 1 minus x squared, is the top part of the curve, and y equals negative square root of 1 minus x squared is the bottom part of the curve. And those are functions if you consider them separately. Okay? And let's say we choose a point where we want to find a tangent line on this unit circle, and let's choose a point we know. Let's try this point up here, which would be 1/2 root 3 over 2 if we choose the 60 degree or the pi over 3 point that we know. And let's say we want to find the slope of the tangent line to the circle at that point. Okay, first of all, we know it's going to be a negative slope, so that's going to see if we're going to see if we're right when we find the answer. But which curve do I have to use? Well, I have to use the positive one because it is the point lies on the upper curve. So I'm going to rewrite this as y equals 1 minus x squared to the 1/2. And now I'm going to take the derivative of this using the chain rule, and we'll get dy dx equals, we go power down, function 1 minus x squared, lower the power 1 to the negative 1/2 times the derivative of the inside, which is negative 2x. And I can cancel the 2's, and I'm left with, if I put things where they belong, negative x in the numerator over the square root of 1 minus x squared. And that's what dy dx is. But I want to find the slope at this point. So I'm going to go such that x equals 1/2. When I plug those numbers in, I'm going to get negative 1/2 over the square root of 1 minus, and 1/2 squared is 1/4, so we can put 1/4 in here. So this would be negative 1/2 over the square root of 3/4, which would be negative 1/2 over root 3 over 2. And I can simplify it one more step here because the 2's cancel, and I get negative 1 over root 3, which is equivalent to root 3 over 3, which is an interesting number to us because that's the tangent at pi over 3. So the tangent value is the slope, which makes sense because it would be the y over the x there, changing y over changing x. All right, so we have the slope now, and we can find the tangent line at our point 1/2 root 3 over 2 by using point slope form. And so we say y minus root 3 over 2 equals the slope, which is negative 1 over root 3 times x minus 1/2. Okay? Well, that's great. That's easy. And we were able to find the slope of this tangent line using the chain rule and solving for y explicitly. But not all functions, as I mentioned a moment ago, can be solved for y explicitly. So there has to be another way for us to be able to find the derivative and be able to find the slopes of the tangent lines to the curves. And there is. And what we do is something called implicit differentiation. And I'm going to start with our easy one here because you better start easy than make things difficult from the very beginning. So I'm going to rewrite our function here as x squared plus some y as a function of x that I don't know. I'm going to pretend I don't know what it is, but I do because we solve for it. So we know what it is. But I'm going to put a placeholder here for that function of x. Okay? And now I'm going to take the derivative implicitly with respect to x. And we don't have to write this every time. I'm just telling you what we're doing here. Okay, so I'm going to take the derivative of this with respect to x. So what is the derivative of x squared with respect to x? Well, that one's really easy. You say it's 2x, and you'd be right. Plus, and then I'm going to take the derivative of this as though it was an implied function of y I don't know, a function of x I don't know. So I'm going to go power down just like I would with a chain rule. Here we go. Power down is 2. Function, which is y of x. Lower the power 1, so that's not prime, that's to the first, times the derivative of the inside. Well, what is the derivative of y? Well, the derivative of y, as we showed up here, is dy dx equals, well, what's the derivative of 1? You go, hallelujah, Mrs. Muller, that is 0, and you'd be right. And we're happy about that. We love those kind of derivatives, okay? Now, this is a lot to carry around here. So what I'm going to do is replace this with y, because that is y. It's just an implied function of x. And now we're going to solve for dy dx. Okay, when we solve for dy dx, we get it all by itself. I'm going to move this over to get 2y dy dx equals negative 2x, just moving it over to the right. And now I'm getting the dy dx by itself by dividing by 2y. And when I do that, I can simplify this and get dy dx is equal to negative x over y. Now that looks a little strange, doesn't it? Because we're used to all our derivatives having only x's in them, like here above. But I can have a y in my implicitly defined derivative here. But I want to find the slope at my point, which we said our point up here was 1/2 root 3 over 2. So I'm going to do my such that bar. X equals 1/2 and y equals, whoops, you can't see that. Let me pull it up a little bit. 1/2 and my y is root 3 over 2. So we're just going to plug in our point. And so what do we get? We get negative 1/2 over root 3 over 2, which looks, I hope, if you can recall from up here, looks a little bit familiar, right? Because that's what we did up here. We did negative 1/2 over root 3 over 2. So that's going to equal, the 2's cancel, negative 1 over root 3. And guess what? We have the same slope as we had up here, which is really cool, in my opinion. Now, what's really wild is, remember, I said that this y of x was a placeholder for the function of y. We didn't know what it was. But what was y? We said y was the square root of 1 minus x squared up here. And if you look at my derivative here, negative x over y, and then you roll your eyes up here and you see the derivative that we had using the chain rule, what do you notice? Well, it's negative x over the square root of 1 minus x squared, which happens to be negative x over y. So we found an easier way to take the derivative without having to solve for y explicitly. All right, and that's how you do implicit differentiation. Now, I'm going to do a whole bunch of examples from the packet where the derivative, and if you'll notice, number 1 in the packet is x squared plus y squared equals 1, which is what we just did. So I'm not going to do number 1, but I'll do number 2 and as many of these as I can. Okay, so let's do number 2. I know this is small, but this is a hyperbola in case we didn't know what the curve looked like. Okay, so we're going to take the derivative of this implicitly. We're not going to solve for y. And so with respect to x, when we take the derivative here, let me zoom in a little bit. So you can see a little bit better. You can see more of my wrinkles, but you can at least see the problem better. Okay, all right, so let's take the derivative of x squared. What do we get? We get 2x. And then we're going to go minus. Now we're remembering that this is an implied function of y, so I have to use the chain rule anytime I take the derivative of y. So it's going to be power down, function, times the derivative of the inside. Remember, the derivative of the inside is going to be y. So the derivative of y is what? dy dx equals, and then the derivative of 1 is 0. And then we're going to solve for dy dx by getting it all by itself. We're going to move, this is be negative 2y dy dx. If I move the 2x to the other side, I get negative 2x. And then we get dy dx equals negative 2x over negative 2y. And we can simplify that a step by saying this is x over y. So if I know a point on the hyperbola, I can find the slope there. Okay, so that's number 2. That was easy. Now let's try number 3. We amped it up a little bit here. Now what's interesting about this one is you notice that I have an x squared y term here. And I've got to use the product rule because those are two things I'm multiplying together. So the derivative of the first term here is, derivative of x cubed, which is 3x squared plus, and now I'm going to use the x squared term as my first term and the y term as the y part of the product of my second term, and use the product rule. And so it'll be first, which is x squared, d second, which is the derivative of y, which is dy dx, plus second, which is y, times the derivative of the first, which is 2x, plus, and then I'm going to take the derivative of 4y squared, knowing that y is an implied function of x, and the derivative of 4y squared would be 8, bring the power down, y, lower the power 1 to the first, and then I have to take the derivative of the inside, which is an implied function of y, implied function of x, which is dy dx, equals the derivative of 6, which is 0. And now I'm going to take all the terms that don't have a dy dx in them and move them to the right side of the equation. Okay, so I'm going to get x squared dy dx plus 8y dy dx equals negative 3x squared minus 2xy, and I like to put my variables in order once I've multiplied them. And then on the left side here, I'm going to factor out a dy dx because we're going to try to isolate it. And I'm left with x squared plus 8y equals negative 3x squared minus 2xy. And then dividing, getting the dy dx all by itself, negative 3x squared minus 2xy all over x squared plus 8y. And there's our derivative. Now it's pretty complicated, but if you knew the point you wanted the slope at, you would just plug in x and y and find the slope. And then you could find the equation of the tangent line once you had that slope and the point. Okay? All right, let's move on. Number 4. All right, I like to do one where we have a negative in front of something that we have to use the product rule for, and I'll show you how I do this. Okay, so the derivative of x squared, I'm going to zoom in just a little bit more. It seems a little bit small to me, and I have my glasses on. All right, so the derivative of x squared is 2x, and then I'm going to use my first part of the product rule as negative 2x and my second one as y. So we're going to use first, which would be negative 2x times the derivative of y, which is dy dx, plus the second, which is y, times the derivative of the first here, which is negative 2. Now, if you do this and you make your first function negative 2x, distributing that pesky negative is taken care of for you. Because if you use negative and then parentheses in the product rule, then you have to make sure you distribute that negative. But I like to say the first function is negative 2x and the second function is y, because then I've distributed the negative without having to think about it very much. Okay? All right, so now let's take the derivative of y cubed. Well, that would be power down 3y squared, lower the power 1, times the derivative of the inside, which is an implied function of x, and the derivative of y is dy dx, equals c. Well, c is just a constant, so we're going to take the derivative of that as 0. Okay? And now I'm going to solve for dy dx. So hopefully you can see that I'm going to factor a dy dx out right away. It's really easy to do. So this is negative 2x plus 3y squared on the left side equals, and I'm going to move the other terms that don't have a dy dx in them. So I'll get negative 2x, and I'm going to add 2y, because I have to change the signs when I move them over. Dy dx equals, and this is negative 2x plus 2y over negative 2x plus 3y squared. I'm just making sure I did that right. Yep, I like that. And then if we knew the x and the y, we can find the slope and then the equation of the tangent line. Okay? All right, number 4. This one has two product rules in it. So we're going to do the first here and the second. So we'll say that that is going to be first, which is x squared, the second, which is the derivative of y, which is dy dx, plus second, which is y, times the derivative of the first, which is 2x, plus, and now I have another product rule here. So it'll be first, which is x, the second, which is power down y, lower the power 1, times the derivative of y, which is dy dx, plus second, which is y squared, times the derivative of the first, which is x, the derivative of x, which is 1, equals, and now I don't have a 0 on this side. The derivative of 3x is 3. All right, and so I'm going to solve for dy dx by collecting those terms. So I'm going to factor out a dy dx in one step here, and we get x squared plus 2xy, because those are the two terms multiplied by dy dx. And then I'm going to move these two terms over to the right side of the equation because they don't have a dy dx in them. So this will be 3 minus 2xy minus y squared. And then solving for dy dx, I just divide by the x squared plus 2xy. And again, if we knew the point, we could find the slope, and we could write the equation of the tangent and the normal lines. All right, number 5. That was number 5. Let's do number 6. All right. I seem to be hung up on the product rule here, which is good, right? Good practice. So this is going to be 5y times to the fourth, lowering the power 1, times the derivative of the inside, which is dy dx, plus I'm going to use the product rule here, and I have x squared, which is first, the second, which would be 3y squared dy dx, because I have to take the derivative of y, plus second, which is y cubed, times the derivative of the first, which is 2x, equals the derivative of 1 is 0. Now, you might be thinking to yourself, well, why aren't I taking the derivative of the inside of x? Well, if you took the derivative of the inside of x with respect to x, you'd get dx, which turns out to be 1. So if that was confusing you there for a minute, you are using the chain rule with x. It just happens to be 1. All right, so let's factor out a dy dx. And we're left with 5y to the fourth plus 3x squared y squared equals, and I'm going to move the negative 2xy cubed to the right. And then to get dy dx here, we're just going to solve for, by dividing by 5y to the fourth plus 3x squared y squared. Again, if you knew the point, you could find the slope very simply. Okay. Questions on that one? So we had to use the product rule again here. So first d second plus second d first, and then solve for dy dx. Number 7. Now we have a product rule here and a product rule here, but now I've amped up the difficulty level a little bit because I've inserted a trig function that has an angle argument of a y. So we have to use the chain rule with this too. And this is an embedded chain because the y is an implied function of x. All right, so here we'll do the product rule for this one first, which would be first x squared, the second, which is 2y times lower the power 1, times the derivative of the inside, which is dy dx, plus second, which is y squared, the first, which is 2x. All right, now we're going to do the product rule with the second piece. This is going to be my first function, and this will be my second function. So first will be x times the derivative of the second, which is, well, this is a composite. So what's the derivative of the outside? It's going to be cosine, keeping the angle argument, times the derivative of the inside. Well, what is the derivative of the inside here? It's the derivative of y, which is dy dx. But I'm not done yet. So plus second, which is sine of y, times the derivative of the first, which is 1, because the derivative of x is 1, equals the derivative of 4, which is 0. All right, so here we go. We're going to solve for dy dx. So we're going to factor that out of the terms that have it. And I'm left with 2x squared y plus x cosine y, right? And then I'm going to move the other terms to the other side of the equation, which would be negative 2xy squared minus sine y. Okay, and then I'm going to get dy dx all by itself. And I would take the right side and then divide it by 2x squared y plus x cosine y. I mean, it looks a little bit scary, but it is okay. If you know the point, you can plug it in and find the slope. And see, this one is definitely a relation, but it's got places where we can find tangent lines, which is really cool. All right. This is a really cool curve. And I wanted you to see it, to draw a picture of it here, you know. Kind of looks like maybe a bat who's, you know, flapping his wings. I don't know. But I like the way it looks, so I figured we'd find its derivative and have some fun with it, all right? Okay, so the derivative of the left side here, well, the derivative of 1 is 0, and the derivative of x is 1. Now, this is a composite on the right side here, but I have to take the derivative of the outside, right? What's the derivative of the outside? Well, it's the derivative of sine, which is cosine, keeping the argument xy squared, times the derivative of the inside, which happens to be a product. So I have to use the product rule here. So first function is x, the second function is y squared. And so the derivative of the first, so we say first, which is x, d second, which is 2y, lower the power 1, times the derivative of the inside, which is derivative of y, dy dx, plus second, which is y squared, times the derivative of the first function, which is just 1. Now, please notice, this is really, really important, that when I took the derivative of the inside, I put it all in parentheses because the derivative of the inside, all of this is multiplied by the first term out here. Okay? And now we have to solve for dy dx. Okay? But it's like it's trapped. Dy dx is trapped by this set of parentheses here. So the way to do this is to distribute this term to these two, which is looking a little scary or uncomfortable mathematically, but it's not difficult to do. So let's do that. So we're going to go 1 equals, well, I'm going to take all of this and put it in front of the cosine. So I'm going to put it in order here. 2xy dy dx times the cosine of xy squared, right? Because I just took all of this and multiplied by cosine of xy squared. And then I'm going to put the y squared in front of cosine of xy squared. Okay, and then this is a lot easier to solve for dy dx because I'm going to move this term over. So let's do that. We'll get 1 minus y squared cosine of x. I should have my equals line up if I can do that. So we'll go 1 minus y squared cosine of xy squared equals 2xy dy dx cosine of xy squared. Okay, and I'm going to solve for this by dividing by every other piece of this term here. So dy dx is going to equal 1 minus y squared cosine of xy squared. That 2 looks a little weird, sorry. Over 2xy cosine of xy squared. All right, so we have now solved for dy dx, and if we know the point, we can find the slope. And yeah, there's going to be some really, you've got some vertical slopes here. That's when the denominator is equal to 0. And you got, do we have any horizontal ones? Yeah, we do. See how we have some horizontal slopes here and here and here and here, and that's when the numerator is equal to 0. So we'll talk about that a little bit later. All right. Well, what I want you to know, though, is just because we have a new technique or a way to take a derivative of an implicitly defined function, or an implicitly defined, not explicitly defined, but or equal to y, the problems are all the same. For example, find the equation of the tangent line to the curve at the given point. Well, they gave us a point, and now all we need is a slope. And to find the slope, I know you all know very well that you have to find the derivative, and then you plug your point in to get the slope. But now this is an ellipse. I like to show this because when you have the xy term in your elliptical equation, what does it do to the ellipse? It rotates it, which is really kind of cool. And we didn't get a chance to talk about rotating ellipses mathematically or algebraically. We talked about them graphically when we did our project. And we found an equation for a rotating ellipse to put in our project. But anyway, we're going to take the derivative of this implicitly because it's not explicitly solved for y. So the derivative of x squared is 2x plus, and now I have to use the product rule here. First is x. The second, well, what's the derivative of y? dy dx. Plus second, which is y, times the derivative of the first, which is 1. Plus the derivative of this 2y, which would be power down, y, lower the power 1 to 1, times the derivative of the inside, which is the derivative of y, dy dx, equals 0, because the derivative of 3 is a constant, so it's 0. And then we're going to solve for dy dx. So dy dx, getting the terms factored out here, x plus 2y equals, and I'm going to move these other two terms to the right side, so it'll be negative 2x minus y, and dy dx is equal to negative 2x minus y over x plus 2y. And I want the slope at 1, 1. So I'm going to go such that x equals 1 and y equals 1. And we're going to plug those in. Negative 2 times 1 minus 1 over 1 plus 2 times 1. So on top here, we're going to get negative 2 minus 1 is negative 3 over, and then 1 plus 2 is 3. So the slope is negative 1. And if I wanted to find the equation of the tangent line, so the tangent line to the curve at 1, 1 is going to be y minus 1 equals negative x minus 1. And since we have Desmos out, let's see if we're right. I'm going to change my curve up here, make this a 2, and I need to make this a 3. And we're going to get rid of that. There's our ellipse. I'm going to make that a little bit bigger so we can see it. All right, I'm going to plot my point. What was our point? Our point was 1, 1. Show the label. And then we're going to graph our tangent line, which was y minus 1 equals, whoop, forgot the 1. Negative, parentheses, x minus 1. Boom. There it is. We found our tangent line to the curve at x equals 1, 1. Okay? Now, what if I took this problem and put a little spin on it and I said I wanted to find where there were horizontal tangents? Do you see how we have a horizontal tangent line here and a horizontal tangent line here? And I wanted to find the x's to find horizontal tangents. Okay? So, horizontal tangents occur when occur when the derivative, right, the slope is equal to 0. Okay, well, when is my slope here, dy dx, and I'll write that down, negative 2x minus y over x plus 2y equal to 0. Well, I have a fraction equal to 0, and the only time the fraction is going to be 0 is when the numerator is equal to 0. So if the numerator is equal to 0, it'll equal 0, but if the denominator is 0, that means that it'll be undefined, which means I have an undefined or a vertical slope, which we have in two places here too. All right. So to do that, what happens here? I get negative 2x minus y. To get a horizontal tangent has to equal 0. And so I'm going to say negative 2x equals y. So y equals negative 2x. But that's not a point. That's not a point. That's a condition. So horizontal tangents occur every time y is equal to negative 2x. But what is the other condition in my problem that has to be true? Well, it has to be on the curve. And we said the curve was x squared plus xy plus y squared equals 3. So guess what, folks? I have a system, which is Mrs. Muller's favorite thing, is a system. And how do we solve systems? Well, we can use substitution here because I know y is equal to negative 2x. So using substitution, I'm going to solve the system. Okay, to do that, we get x squared plus x times negative 2x, because that's y, plus negative 2x quantity squared equals 3. So let's do some math here. So this is x squared minus 2x squared plus, if I square both of these, I get 4x squared equals 3. And so I'm going to get 2x squared, so 3x squared. 3x squared equals 3, because this would be 5 minus 2, okay? So we get x squared equals 1, and x equals plus or minus 1. Oops, sorry, you didn't see that. So how do I get the y that goes with plus or minus 1? Well, we're going to recall that y equals negative 2x. So when x is positive 1, y is negative 2. And when x is negative 1, y is positive 2. And so let's see if that works on our graph. Let's plot our 2 points. We have 1, comma, negative 2, and 1, negative 1, comma, 2. And does that look like where the horizontal tangents are? Well, indeed they are. And if I want to write an equation for a horizontal tangent, the slope is 0, and so it's going to be whatever your y value is. So it's going to be, the tangent lines are going to be y equals 2 and y equals negative 2. All right. And so if I wanted to find out where the tangent lines were vertical, what would I do? I would set the denominator equal to 0 and do the same thing, solving a system, and find the points. Okay. All right. Let's see how many more problems we got here. All right. I'm going to let you try number 10. So pause the video and you try number 10, and we'll compare at the end. All right, so you're back from your pause. So this is going to be 2x, taking the derivative, plus first, which is 2x d second, dy dx, plus second, which is y, times the derivative of the first, which is 2, minus 2y dy dx, plus 1 equals 0. And this is a rotated hyperbola, which is really pretty cool. All right, so dy dx. Factoring that out, I get 2x minus 2y equals negative 2x minus 2y minus 1 dy dx equals negative 2x minus 2y minus 1 over 2x minus 2y. So let's see here. That looks good. All right. And then we want to find the slope at 1, 2. Such that x equals 1 and y equals 2. If I plug that in there, we're going to get negative 2 times 1 minus 2 times 2 minus 1 over 2 times 1 minus 2 times 2. All right, so this is negative 2 minus 4 is negative 6 minus 1 is negative 7 over, and then this is 2 minus 4, which is negative 2, which is negative, or 7/2. So let's see if that works. I'm a little suspect of my numbers. I probably made a mistake this early in the day, so let's try it. Y minus 2 equals 7 over 2 times x minus 1. All right, so let's graph this thing really quickly. If my computer will go quickly today. Probably not. All right, so what do we got? We got x to the second plus 2xy minus y to the second plus x equals 2. There's our nice, lovely looking parabola. Oh, I want to take away these labels. All right, and then I want my point was 1, 2. Yes, and that's good news. It is on the curve. And now I want my tangent line, which is y minus 2 equals 7 divided by 2, parentheses, x minus 1. Yay! So my math, adding and subtracting in public work today. That's good news. This is the tangent line at 1, 2. All right? All right. So the one thing I did want to show you was finding the derivative on the calculator really quickly. Okay? Our TI-89 has an amazing function. Pardon the pun, right? Amazing function. I'm going to go to the home screen here, and we're going to go to the calculus menu, which is F3. And you can't, when we do implicit differentiation, you can't use this differentiate. You have to use another function. And instead of scrolling down all the way to 9, I'm going to scroll up. And you're going to see something called impdiff, which is the shorthand for implicit differentiation. So our calculator has a function to do implicit differentiation, which is really cool. And I dare the 84 to do that. You know how I say that all the time, and I actually love it. Okay, so what happens when you press that key is you get impdiff, and then we're going to type our equation in here, the one for our hyperbola, and we're going to go x to the second plus 2x. Now this is critical right here. These two are being multiplied, the x and the y. And so we have to put a times between variables that are being multiplied, or the calculator doesn't do the calculation correctly. So it's 2x times y minus y to the second plus x equals 2. And yes, we're putting an equals there, comma. Now you have to tell it the independent variable, which is x, comma, and then the dependent variable, which is y, and then you close the parentheses, and then you press enter, and whoop, what did I do wrong? Oh, I used the wrong symbol there. See, I'm human. We're going to put a negative, right? Oh, wait. It's times y. I didn't put the times y. There we go. Of course, I have to do something wrong every time I do a video, right? Never a dull moment. All right, so does this match our derivative? Well, this calculator factored a negative out, but that's fine. That matches our numerator. And they factored a 2 out of the denominator, which is also fine, and it matches. So there we go, which is pretty cool. And then if I wanted to have the slope there, we could use the such that bar at the end of our command. X equals what we said? 1. Okay, and then we're going to go to the catalog. Do you see the catalog button right here? Catalog, and we're going to choose and. What else is true? We want y to be equal to 2, right? Because we will have x is 1 and y is 2. So we use the such that bar, x equals, and we go to the catalog and grab and then type y equals 2. And you get 7/2, which is really cool that the calculator can do it for you. Okay? All right. Well, you guys have a great rest of your day, and we will talk to you next time.